In this session I'm going to point out a little more in detail this revolutionary idea in quantum mechanics that, strictly speaking, the idea of the conservation of energy is not strict. And if you think about it, that is quite a revolution. So remember the earlier session we were talking about the interpretation of AM squared, and we interpreted that to mean the probability of a transition, switching from state UK to UM. Now, in the context of energy eigenstates, so state UK would correspond to energy level EK, and a switch to state UM would correspond to switching to a state E of M, an energy level E of M. Now, we had a formula, we had a graph, if you remember from earlier session, that took the form of a psi squared, of rather complicated expression. But on this axis you had omega, your frequency, here, omega, and this axis was the sine squared term, which gave you sort of a rather peaked, looked a bit like this. And that sine squared term gave you, that was the essential term in the AM squared, which is the probability of a transition from state K to state M. And the difference in the energies EM/EK was defined as h bar. You get three bars here, so by definition is h bar omega mk. So for that particular frequency. Now, as I was saying in the earlier session, that peak, that your AM squared, effectively your sine squared, various expression, that term is not a delta function, right? It's not infinitely thin and infinitely tall. Its width is proportional to 1 over t. Remember, t is the time range over which the interaction, the switching, the transition is to take place, right, from 0 to t. And the width is of the order of 1 over t, and the height I think was something like of the order of 4 over t squared over 4, something like, anyway, yeah, I think t squared over 4. So it's not a delta function, right? It's not infinitely thin. And so that means that, now remember along this axis you had omega here. So this, and the width of that peak was proportional to 1 over t. So that means this omega here, which is roughly equal to this, because it's this AM squared is effectively 0 outside that the range of the peak, and the peak width is of order 1 over t. So this is approximately true, but think about it, it is not strictly true, right? This is only approximately equal to this. Now this by definition is equal to this. These two energy levels are accurately known, okay? So this is accurately known, hence this is accurately known. But this omega here has a finite width. It's not exact. It is not exactly this, right? So in other words, energy is not strictly conserved in this context, okay? Because this omega here is not strictly equal to omega mk. Now this value here, omega mk, that was the middle term of your peak. That was the actual peak value, if you're right. But this AM squared, this sine squared term, came down either side of this value. So you could have, you can still get a transition occurring in that range, that proportional 1 over t width of the peak. Right? You could have an omega value in that range that's roughly equal to omega mk, but not exactly. And so that means that you can get a transition from one energy to another even though omega is not exactly equal to this. So you don't have conservation of energy. Now that's quite radical if you think about it. So from this we will derive an alternative form of the Heisenberg uncertainty principle in the form of a delta E delta T, somewhat similar to delta P delta X earlier, and we can do that now, right? Right. So just saying a bit before, this peak, this sine squared term, it's quite sizable because as t becomes quite large, if it's a slow transition, the range of time in which the transition takes place, from 0 to t, if t is quite large, then the height of that peak goes up as t squared, right? So the probability of transition is quite large. Okay? So the range of this omega is proportional to 1 over t. Now, if you multiply both sides by h bar, you'll get h bar omega, but that's approximately equal to this, right? Which is the difference in the energy, delta E. Okay. So h bar omega, but omega is proportional to 1 over t. Okay, so h bar omega is proportional to h bar over t here. Okay, but h bar omega is the difference in the energy, delta E. Therefore, delta E is proportional to h bar over t. Okay. Now, you don't know exactly during that interval 0 to t the transition, the switch takes place. Okay, so just consider then this t is the duration, the time interval. The transition occurs somewhere in that time. It's in that sense vague. Okay, so that's what your delta. You can write that as your delta t. In other words, the transition occurs during that time period, delta t, sometime. But within that period, you don't know when. Right? That's so you can label this t as delta t. That's the time period within which the transition occurs, and bring it over, and you'll get delta E delta t is proportional to h bar, which is here, which I've put in a rectangle because it's important. Right? So this is the energy time uncertainty relation, Heisenberg uncertainty relation, the hub, in the delta E delta t form, right? And it's somewhat similar in nature. So you've got the product of two uncertainties as usual, okay? But in an ET rather than a PX form. So also quite famous. Now, how to interpret this? Well, one way which gets used quite a lot is that in a sense you can have a quantum system that borrows energy from some other system, I guess. It borrows an amount of energy, delta E, and so long as it pays it back, so it's it's sort of like a bank loan. So long as it pays that energy, delta E, back within period delta T, then that's allowed. Because in quantum mechanics now, conservation of energy is not strict. It's subject to this famous energy-time uncertainty relation. Okay, so one way to interpret this is a system can borrow this amount of energy so long as it pays it back within this amount of time. So that system then is violating conservation of energy to this extent, right? Now, from the math, it could borrow a lot of energy, quite a lot. So your delta E could be large, provided it's paid back very quickly. Okay? So in other words, the smaller delta T is, the larger your delta E can be. Right? That's just because this is a Planck's constant, with emphasis on the word constant. Okay? So as this goes down, this can go up, right? And vice versa, of course. Right? Now, Now that's rather crude, but you can use that kind of thinking, that idea, for example, to interpret various phenomena in quantum mechanics. For example, the tunneling phenomenon, that we did quite a few lectures back. You could reinterpret tunneling as your system that's doing the tunneling, in a sense, borrows energy, and then instead of tunneling, actually jumps. It just jumps over the potential hurdle, the potential barrier. As long as it does that, within less than delta t, and so it doesn't go through the barrier in a sense. It goes over it. It sort of high jumps the barrier. That's it's a reinterpretation of tunneling using this kind of thinking. Well, that's the end of the session. So the main idea, now I've put double bars here and arrows to really emphasize it. The notion of conservation of energy within quantum mechanics is not strict. It's approximate, of course, but it's not strict due to the finite width of the transition probability, that peak in the sine squared term that we had from an earlier session. Alright? And from that we derive this very important energy-time uncertainty relation, Heisenberg uncertainty relation. Okay? So two main ideas of this session.